In this video, I'll talk about power flow, steady state, basically steady state. Steady state power flow. And I'll just give an overview. I'm not going to go through the detailed derivation, that can be separate videos, but just kind of an overview and talk about some important concepts. So what is power flow when we talk about power flow? So the power flow basically is the calculation of voltage, magnitude, and phase angle at each bus. When you think about a large system like the North American system, Eastern interconnection, for instance, you have like 10,000s of buses, substations, and so it's a very huge system. So we want to know what the voltage is at every single bus, and angle also. And this is done, under a balanced system. That's what we mean by steady state. In other words, everything is balanced. We do this power flow. So balanced, three-phase, steady state conditions. Positive sequence only is involved here. Impedances. So no negative, no zero sequence, because that would be very complicated, to take into account and balance conditions. But power flow, basically, when you have a three-phase, for instance, everything is balanced, everything is under steady state. It's like perfect conditions, kind of. So power flow model is really a snapshot. In other words, you say, as if you stop time and you say, okay, at this time, I'm going to look at the loads, what they were. For instance, if you're looking at peak load, for instance, like summer, you say, I'm going to take, this is the model that I'm going to kind of run power flow on. So the power flow will give you a result just for that particular snapshot. So, again, we assume the system is stable and it's operating at 60 hertz. So real reactive power flows in transmission lines and transformers, as well as losses, can be calculated. They're kind of like a byproduct of this power flow. The starting point of a power flow, typically a single line diagram that shows the system topology, like what's connected to what, and like if there's anything that's in parallel, transformers, how many transformers you have connected between buses, from which input data for computer solutions can be obtained. Input data consists, bus data, voltage, other things, like what is the rated voltage, and so transmission line data, resistance, reactance, capacitive susceptance, transformer data, impedance, ratings, and so on and so forth. So when you have a linear system, you can use direct solutions, like Gauss elimination and back substitution. So if you have a set of linear algebraic equations, if you put them in a matrix format, you have a matrix A equal to some vector X. So the product will be equal to vector Y. Example, when you have impedance, you take the system and you put it in a vector form, all the impedances, then currents. So impedance times current is equal to voltage. So you can do that in a kind of matrix format, Or if you don't want impedance, you can do admittance. Current is equal to admittance times voltage. Now, matrix A, it will have some entries. So like the first kind of entry, A11. So basically row 1, column 1, column 2, to column n, and you do the same thing for rows. So it's n by n matrix in this case. Then X would be a vector. So you have n entries or rows. The same thing with Y. But in this case, for instance, like in this case, you would have to know at least two. you know impedance and voltage, you can calculate current, or you know impedance and current, you can calculate voltage, and vice versa. So it's so again, instead of like a general form here, so current, for instance, you just have all the currents in your system in a vector form, then the admittance would be kind of the matrix, and voltage is a vector. So if the system is linear, you can use nodal equations, KCL, KCL, KVL, mesh current, so on and so forth, to calculate, current or voltage, or generate. But the problem is that with the power system, generation, power plants are represented as power sources, not voltage sources behind impedances. So in other words, when you have a generation connected to a bus, it's injecting P and Q, in some cases, and I'll talk about, because, voltage, so when you have P and Q, now it's no longer linear. Because typically what we have seen in circuit analysis, we have some voltage source behind some impedance. Well, in that case, you can use, that's why we used Ohm's law, KCL, and all other nodal equations. But in a power flow, the problem is generation is not represented as voltage sources behind impedances. So they become non-linear. Also, the loads are represented as PQ. So if you have a load, for instance, it's going to consume some P and some Q. So now it's no longer, it's not resistance and impedance. So nodal equations, if you have this form in the form, for instance, current is Y bus times the voltage vectors, But the problem is, in a power system, we don't know current, we do not know voltage. All we know is the Y bus. Well, current injected, each bus is unknown, voltage is unknown, so we cannot solve this equation. So then what do we have to do? So we have to use some other methods, that I'm going to talk about. So if I have bus, like at bus I, for instance, you're going to take, so the current, the injected current, for instance, total injected current at this bus, if I call that I is this summation here for anything that's connected to that bus. So it's, because you're going to have some lines, for instance, connected to that bus. So lines connecting this bus I to other buses, K, for instance. So you're going to take the admittances between that I and K, only if there's a connection, so they have to be connected basically, times the voltage at bus K. With K is 1, 2, 3. How many you have? We know complex power delivered to bus I, S, is P plus JQ, or the voltage at bus I times the injected current at I with conjugates, because we're talking complex numbers here. So then S is in this form here, or this form, from what I showed, which is also, sorry, this should be I, which is, because again, so VI, and what is II? It's this equation here. So I'm just doing substitution, because this one here is II. So nonlinear equations that involve, and obviously if you go through it, because all these are complex, they're going to involve cosine and sine. So they are not linear. So that's in this simple kind of derivation, I start from this nodal equation here, and I arrive to something that's really hard to. It's impossible to solve, using linear equations. So then, how do we solve this? So we have to use some iterative methods. So the common ones are Gauss-Seidel, and really Gauss-Seidel is kind of old. It's no longer used. Any power flow program will have some of them, not all. Some of them, they don't even bother programming Gauss-Seidel because it's very complicated, it's tedious, plus you have to maintain it. If you have that code, you have to maintain it. You have to tune it to become more stable because if there are like non-convergence issues, or convergence issues, you have to tune it, and that's just, you are maintaining something that no one is using basically. So some power flow softwares will not even bother have Gauss-Seidel, but it's a method. But the most common one is Newton-Raphson, and Newton-Raphson have different versions that I'm going to talk about. So first, let's just talk about the bus categorization in a power system. So each bus K falls under one of the three. So either swing bus, some people call it slack bus. So in a power system where it's huge, so if you have like a Eastern interconnection, for instance, Eastern interconnection, so the entire system might have like a swing bus. And each area, because within that you will have like either utilities or states, but basically you have like multiple areas. So each one will have its slack bus, for instance. So slack and swing kind of mean the same thing. It's just an industry terminology, so don't be confused by that. And I'll talk about why we need a swing bus. Load, you can also have load or PQ, basically load is represented as P and Q, or voltage controlled P and V, and I'll talk about it. So let's start with swing bus or slack bus. Swing bus really does not have any physical meaning. In other words, we don't say a generator in Florida will be our swing bus, and that's not how it works, because when you have when you need generation, all generation is gonna be used to the appropriate level, or so it's not. So swing bus is just a mathematical concept. Swing bus provides a reference for bus voltages and angles, because as the power flow iterates, it's going to calculate voltage with reference to something, angle with reference to something, and that's to the swing bus. Swing bus provide losses incurred in lines and transformers, because as it iterates, any mismatch in losses, because at any given time, generation has to equal load plus losses, because you're going to have I squared R losses in lines, transformers, and other things. So if load decreases, that means generation will have to decrease accordingly. If generation or load increases, generation has to increase. Or if everything is the same, but now you have like losses, somehow you have extra losses because you have generation, the same load is the same, except topology change. For instance, there is an outage on a line, but it's not going to cause any load to drop. So losses could change, so generation has to adjust appropriately. So need swing bus, since losses are not known until a solution is obtained, because the power flow will go through, will calculate different things, but you're not going to know what the losses are until the solution is done. So that's why you need a swing bus. Typically, there is one slack bus for, but again, for large systems, you might have a swing bus for the entire power flow, and you have to have at least one. Otherwise, the power flow is not going to solve, it's not going to work. And some areas might have their own swing bus, slack buses. You know, again, it's just terminology. So, but for our purposes, we will refer to bus number 1 as the slack bus. You know, it's just something I chose. You know, it doesn't have to. So swing bus will have, so voltage is determined, is known basically. You know, for instance, 1 per unit or 1.05 per unit, whatever is scheduled, you know. And the angle is known, so theta 1 probably is 0 degrees, so it's known. So kind of here's to give you an idea. So this is an input data. So what the load flow program will will calculate P and Q for the swing bus. If you have a load bus, P and Q are input data because we know how much the load will consume or need. So those are, but the program will go through and calculate V and delta. At any given time, you have 2 unknowns and you have two known 2. So I know these 2, but I don't know these 2. I know V and delta, but I don't know P and Q for the swing bus. So voltage controlled PV bus. So P and V are input data. So this is typically if you have a generator. Generator that is not designated as a swing bus. Because swing bus, V and delta are, V is known, but a generator that's not a swing bus, P and V will be known. Then the program will calculate delta, the angle, and also Q. You could have a StatCom, a capacitor bank, or any other voltage control like a device capable of providing VARs or voltage support. The only thing is if you have a capacitor bank, for instance, or a StatCom, P is 0 because they don't provide any real power. So the load flow program will calculate Q and delta. Examples, you know, you have generator bus that are not swing buses. Switch shunt capacitor buses, load and generator buses, StatCom. Another example is bus where you have a transformer that has tap changing. So max and min VAR limits that the equipment can supply are input data because you have to input those, so and you want the program, hopefully, as it calculates Q, for instance, it does not exceed the min and max of that. You know, if you have a generator, for instance, that's a PV bus, you want this generator will have Q min that you cannot go below, and will have Q max. So as a generator, as the load flow calculates Q at that bus, it will go back and check, is this Q smaller than the Q min? If the answer is no, then that's good. It will also check, is that Q greater than Q max? If the answer is no, that means it's within the tolerance, then we're good. So then what it will do, it will set QI. If somehow the min and max are exceeded, then it will set that the calculated Q to Q min or Q max. But if it does not exceed the limits, then it will use that Q that's calculated. So if this case here occurs, Q is equal to Q min or Q max, then the bus model as PQ is converted from PV to PQ, load bus basically, because Q is set to either Q min or Q max, whatever is calculated. So if you have a swing bus, you have these 2 unknowns, PQ load. So the same thing here. But if you have a PV bus, like a generator basically, or a StatCom capacitor, if Q exceeds the limits of that device, but what do I mean by limits? Q min or Q max. Then PV is changed to PQ, and the Q is set to the limit. So modeling load flow and power flow. So so for a load, you can model it different ways. Like one way is constant power, which is typical, constant power load. Basically, what do you mean by constant power? S is constant. It does not vary with voltage or current. So S we know is V times I, so it's constant. Then if we solve for V, is constant times 1 over I. Basically, current increases, voltage decreases. From this equation here, the load power is held constant. That means we don't care what the voltage current, as long as the bus voltage is above the specified value. Typically, the voltage, if it's above 0.8 per unit or 80% of the rated voltage, the constant power will work. So the program will have a setting in this case. So you say, if you plug or if you plot power, basically either P, Q, or S with respect to voltage. So as voltage increases, so power is going to start increasing. So it's not going to become constant until you reach a certain voltage. Then it will be constant because, and practically speaking, when voltage is below 90%, 0.9 or 0.88, it's not going to work, But from a power flow modeling or solution perspective, so the power flow tool or software will have a setting where you can say when voltage is below this voltage. So if you enter 0.8, for instance, it's gonna hold the constant power as long as that voltage, calculated voltage, is above 0.8 per unit. But if it's not, it's going to reduce load, and it will report that. It will tell you at this bus, I had to reduce load by this amount in order for the power flow to solve. Otherwise, if you imagine you have a model that has like 100,000 buses, like one bus not meeting that, if you put like 0.9 for instance, and somehow there is a bus that has a very low voltage, it's going to diverge. It's not going to converge. So one bus will prevent the entire model to solve, But to get around we don't want that, At least having a solution is better than not, At least if it gives you the solution and it tells you at this bus, I had to drop load, shed load, basically, in order to solve, it's better than not solving at all and you have no idea why, So it will give you a setting, where you can set this. You can set to 0.7. It depends on what you're doing, 0.8. So load is reduced if bus voltage goes below this value, load shed. And again, it will report that. It will tell you at bus number, for instance, 20, P, Q, this is what it had to reduce it to, to solve. As current draw is increased, voltage drops, So again, if you plot current versus voltage, as when you have voltage is low, current is high. So current is not going to decrease until voltage go above a certain value, So constant power, this is something important to keep in mind. When voltage is below a certain value, the power flow may not solve, So you might have to reduce that value in order for it to solve. And again, it will tell you how much load had to be reduced for the power flow to solve, And and then you go back and say, okay, is this a reactive power deficiency issue? In other words, do I need a capacitor bank? And you can go through the simulation, like add a capacitance, reactive power, for instance, and see if it solves, if it's an issue, basically, or if it's just a mathematical issue. But that's when you have constant power, this is something important to remember. So now constant current. So in other words, the current is constant. So again, if we go back to the same formula, we hold it the current constant. So current here is constant. So what this tells us is as voltage increases, S increases and vice versa. For bus voltages below a certain value, again, say 0.7, from a mathematical perspective, current will be reduced. Obviously, practically speaking, you know, when voltage goes below a certain value, you know, 0.9 per unit, you're gonna start being concerned, you know, like you have to do something, you know. 0.7 is just from a mathematical perspective. Again, current versus voltage. Again, once voltage reaches a certain, let's say 0.7 per unit, for instance. So current will not, below this value, you see it's not constant. So it's not going to become constant until you go above that. Then you see as voltage increases, PQ has kind of increased. Constant impedance. So this is another way you can, so impedance is constant basically. Again, we know Z is V squared divided by S, and we hold that constant. So S decreases with the square of voltage in this case. So Z also is V divided by I, constant. V decreases with same ratio as current. So these are just some important concepts to remember, you know, when you're talking about power flow. So the next video, I'll talk about Gauss-Seidel methodology, then kind of give a numerical example, then we'll talk about Newton-Raphson. Thank you.